Hey guys, what would you do if I decided to, shove this problem into your face today? I mean, it looks like a pretty fun problem to do, right? Right? A nice little competition style question that you can, have some fun with. Well, let's see what a problem solver would usually go through to solve such a, well, a problem, I guess. All right, so of course, to solve such a problem, the first step is to understand it very, very well. Now, of course, in this case, it might not be too hard to understand it. I mean, like, we're given three initial conditions, we're given a recursive formula, and then we're finding some sort of ratio. Now, of course, as I said, it's not too hard to understand what it's asking for, but if you pay attention to the recursive formula, this is not really a usual recursion that you'd get. It's not like, an is equal to an minus 1 and then plus 1. It's not something simple like that. So you might be wondering, how are you supposed to use this formula effectively, right? Well, if you're not sure of what to start with, if you don't have an obvious leeway, well, it's probably best to just start simple and try to observe perhaps a pattern within the sequence. Start off light, right? Don't go into the deep end right away. So in this case, playing around with the formula, what if we plug in n equal to 3? Well, then the formula would tell us that a3 times a0 plus a1 times a2 over a2 times a0, this is equal to 2a2 over a1. And of course, we're given a0, a1, and a2, so we can just plug them right in. That's 1, 3, and 27. So therefore, we have a3 times 1, and then plus 3 times 27 over 27 times 1 is equal to 2 times 27 over 3. Now, I hope you see now how the recursive formula works. You realize that this recursive formula requires you to solve for the variable, and that's how it functions. Now, of course, in this case, you can easily solve for a3. It's just basic algebraic rearranging. So a3 is equal to 2 times 27 over 3, right? You have to multiply this 27 over, and then minus 3 times 27. And of course, you can just evaluate this to be 405. Okay, well, that was nice. You got the value of a3, but think about it for a second. Do you think you can really feasibly continue with this strategy of finding a pattern through brute force computation? Maybe take a minute to think about it. Right, well, it's always important to reflect on your methods before actually proceeding with them and maybe finding it that it doesn't work at all. And in this case, notice that you got a3, that's very nice, but what about a4? Well, of course, you can do the same thing, right? Just plug in n equal to 4 instead of 3 over here, but you see that a3 is already 405, so a4 might get larger, right? And if it's going to be larger, well then even if it doesn't get larger, well, you might imagine that later down the line, the calculations might get further more tedious, and honestly, it might get to the point that the calculations are just so not convenient that you're just gonna want to scream. So it might not be exactly that viable of a method to brute force calculate terms and try to find some sort of trend. So in this case, you might want to reset. And don't think that's a bad thing. Resetting due to a method not really being that effective is never a bad thing. But of course, if you're going to reset, well, it's always good to consider the problem once again. Did you miss some sort of breaking point that you initially missed, right? Because in this case, if you were to take a look at this problem, what stands out to you? Well, okay, for you, it might not be the same thing as me, but if I were doing this problem, I would probably take a look at this recursive formula and go like, okay, bro, this is extremely complicated. This is a pretty messy formula that they gave us. And honestly, if I were, doing this on a contest, I wouldn't know. But my first instincts would probably to go like, okay, wait, is there a way to maybe simplify this formula so that it looks a lot more manageable? And in this case, the first simplification might not be obvious, but just try anything, right? This left-hand side is a fraction. Well, why don't we try splitting that up? If we split up this fraction, well then we just get an times an minus 3 over an minus 1 times an minus 3. And then this is plus an minus 2 times an minus 1, right? We're just splitting up the fraction according to the denominator, right? And this is still equal to 2an minus 1 over an minus 2. Now, once you split them up, you see, if you just take a look at this equation for like 5 seconds, you can see that you can conveniently cancel out these terms, right? And that little feeling of progress could mean something. It doesn't mean that you're always on the right track, but if you see something convenient, just go for it. Just try anything, right? so this becomes this equation, correct? Now, once I write this all out, take a look at what we have in front of us. This, it might not look like that we can further simplify this, but pay attention to this equation, especially the structure of each individual term. What do you notice? Take a minute to think about it. Alright, so notice that each of these three terms, okay, for the right-hand side, ignore the 2 for a second. So if you pay attention to each of these three terms, you notice that they have a common form. They can all be written in this format. They can be written as ak over ak minus 1 for some positive integer k, right? Now, of course, okay, it doesn't have to be positive integer because there is a0, but you get the point, right? Now, to illustrate this, this over here is k equal to n. This over here is k equal to n minus 2, and this over here is k equal to n minus 1. Now, if we have this common structure across all three terms, we can use this to our advantage to simplify this more complicated looking equation. And this is through defining a new sequence. That is, we can let bk equal to this, and therefore this equation just nicely simplifies to bn plus bn minus 2 is equal to 2bn minus 1. This over here is a lot more simple looking, and it looks a lot more manageable to use. However, what do we do next, right? That should always be your next question. If you don't see something that is all that much more simpler to your desire, ask yourself, what do you do next? Well, in this case, we've just applied a pretty elegant technique, right? We just defined a new sequence based on a common structure, and then we were able to simplify it to something more convenient, right? Now, whenever you use such a such an elegant technique, try to think if you can reapply it. Of course, it might not be in the exact same fashion. Maybe you have to do some work before doing that, but try to see if you can apply the overall same technique to further advance your progress. Take a minute to think about what you can do with this equation. Alright, well, in this case, you can't exactly do a direct substitution to simplify, but you can rearrange the equation into this, right? You just move a copy of bn minus 1 to the left and move this bn minus 2 to the right. And now, what do you see? Well, each of these two terms, they have a common form. They can be written as bk minus bk minus 1. And if they have this common form, we again can do the same thing. We let this be equal to ck, and therefore this equation just nicely simplifies to cn is equal to cn minus 1. And there we have it. This is a super looking equation, right? So in this case, we have cn is equal to cn minus 1. Well, what does that mean? Well, that would mean that if this term is equal to the previous term is equal to the previous term, and so on and so forth, well, this would have to imply that cn is a constant sequence, right? So therefore, if you want to determine this entire cn sequence, well, all you gotta do is compute some early term, and then you just get the entire sequence, right? Now, are we gonna go compute c1? Are we gonna do that? Take a minute to think about it. Okay, well, in this case, if you were to actually compute c1, well, this is equal to, well, from this definition, b1 minus b0. And from our previous definition of bk, right, this is equal to a1 over a0, and then minus, right? So this b0 is a0 over a sub negative 1. And well, you see that a sub negative 1 was never defined in the problem statement. So obviously, C1 doesn't exist here, and therefore we cannot compute C1. Now, of course, this would mean that we can just compute something like, C2, right? And this should fix the issue. However, it's always helpful to consider domain issues, because if you don't consider them, especially for like a more nastier problem in the future, you might end up landing in a whole world of confusion, not knowing why in the world something's not computable. In this case, yeah, we'll just move to C2, but it's always good to have a keen eye on domain issues. So in this case, C2 is equal to B2, right, and then minus B1, and then this is equal to, from our B definition, this is A2 over A1 minus A1 over A0, and we're given A2, A1, and A0. That would be 27, 3, and 1, respectively. So we can just, plug them straight in. 27 over 3, and then minus 3 over 1. This is just going to evaluate to 6. So therefore, C2 is equal to 6, and from this recursive formula, we get that C2 is equal to C3 is equal to C4 is equal to literally every term in the sequence, right? And this is all equal to 6. Awesome. And so now we've determined the entirety of this constant sequence. What next, right? Great, we've determined a nice constant sequence, but what do we do exactly? Well, now is the time to introduce a pretty cool concept, and this is one of the key concepts that we will be taking a look at for this kind of problem. It is called telescoping. I want you to imagine as if you had a sequence of terms, and I asked you to find something like the sum or product of all of them up to a certain point. What would you do here? Well, obviously you wouldn't do direct computation one by one, right? That would be very tedious. So this is exactly where the method of telescoping comes into play. You see, if we were able to write each of these terms in another form, and then substitute that form inside, well, the intermediate terms could potentially cancel out, leaving us with a very easy sum to deal with. For example, consider the sequence an is equal to 1 over n times n plus 1. This is a very classic telescoping example. If we were to write this into 1 over n minus 1 over n plus 1, well then this is extremely useful for finding a sum like a1 plus a2 plus a3 plus all the way to a100. You see, if we were to substitute this form into each term, well, the intermediate terms would cancel out. The positive term cancels out with the corresponding negative term, right? This is exactly what telescoping is all about. This method gets its name because this is literally how a real handheld spyglass would work. Basically, you have a bunch of intermediate lens, but as you look through the spyglass, all those intermediate lenses will kind of cancel away, ultimately reducing your vision to as if you were looking through one giant lens. In the same way, this method cancels out all the intermediate terms, often leaving you with only the head and tail terms. Alright, well, now that we know what telescoping is, let's try to apply it. And here I'm going to show you why telescoping can be so incredibly useful for constant sequences. First, I'm going to get rid of all this, calculation up there. So basically, why is telescoping so useful for constant sequences? Well, I want you to consider the sum C2 plus C3 plus C4 plus all the way to Cn. What is this equal to? Well, each of them is just equal to 6. No brainer, right? And how many terms are here? Well, there are n minus 1 terms, right? So that's n minus 1 and then times 6. Now, what can we do with this? Well, it's always helpful to go back to the defining features of the objects that you're using. In this case, what is the defining feature for the C sequence? Well, it's right over here. We can substitute each of these terms with the B definition. So C2 is equal to B2 minus B1, right? And then this C3 is equal to B3 minus B2, right? And then plus, I'm just going to write one more, right? There's C4 is equal to B4 minus B3. And then, let me write that 3 better. And then plus all the way to, I'm actually going to write the second to last term. So the second to last term is Cn minus 1. And this can be written as Bn minus 1 minus minus bn minus 2, and then plus this cn is equal to bn minus 1. And this is still equal to n minus 1 times 6. Now, what is the power of this? Well, because this was constant, right? The sequence was constant, we could write the sum in one way, but then we could also replace this constant sequence with its defining definition. And the defining definition, defining feature, I would say, rather, I'm just saying the same word twice, right? The defining feature is exactly what helps us perform telescoping. Here in this case, this b2 cancels out with this negative b2. And this b3 cancels out with this negative b3. And you can see that this b4 will cancel out with some future negative b4. And all the way until this, you can see that this bn minus 2, this would cancel out with some previous positive bn minus 2, right? And this bn minus 1, this would cancel out with this negative bn minus 1. And there we have it. That is our telescoping. And in the end, we're left with just bn, right? And then minus b1. And this is equal to n minus 1 times 6. Super convenient. Now we can basically get bn because this b1 we obviously know. We can just calculate it by brute force. That's 3 and 1. There we go. So therefore, in this case, bn is equal to bn minus 1, and then, times 6 plus 3. And therefore, bn has a closed formula that we just derived. Now, what can we do with this? Well, go back to your problem. What do you want to find? You want to find a 2026, I'll erase this circle, a 2026 over a 2025. Now, go back to your defining feature for b. Remember, the defining feature for bk is ak over ak minus 1. And this is super convenient because we are literally asked to find a ratio of 2 consecutive terms, and this bk is literally equal to the ratio of 2 consecutive terms. So therefore, we just substitute that in. So that's an over an minus 1. And there we have it. All we need to do is to plug in n equal to 2026. Evaluates to 12153. And therefore, this is our final answer. Whew, a lot of work, right? But in the end, you see that a whole series of thought processes led us to this final answer. And to summarize what we did, well, first of all, it's really important to notice structure. Structure within the equations often makes it extremely useful to define a new object and to replace the equation with a new object to make it look simpler. And then, of course, telescoping, especially telescoping with constant sequences. You're able to write the sum of a constant sequence in one way, but then you can also rewrite each constant term with its defining equation, right? So yeah, thank you very much, guys, for watching this video. If you found it interesting, if you enjoyed it, then please do consider dropping a like and subscribing. Thank you very much. Bye.